Greetings! Welcome to Electronics 2, lecture number 4. I am Razavi. Today we will take one last look at cascode structures and go over some additional examples of how we analyze cascode circuits and cascode amplifiers so that we are really comfortable with this topology and the equations that govern this topology. So we're going to use that equation that we derived last time, or we talked about last time, and apply that to some additional examples. And then we will finish up with building a cascode amplifier whose input is a p-type device rather than an n-type device. So for example, it uses a PMOS transistor to sense the input voltage and then generate a current and pass that current through the circuitry so that we have a voltage at the output. So these will be what we will cover today. Okay, now before we go there, let's review what we learned last time. Last time we started with this equation, which is, as we have seen, quite powerful in analyzing the voltage gain of various circuits based on the transconductance of the circuit and the output resistance of the circuit. And we started applying that to the circuits that we already know. We said, well, if we have a simple common source amplifier with an ideal current source as the load, then the voltage gain is minus GMRO. So that's about 10, maybe 5, maybe 8 these days. So it's not a whole lot. And then we said, okay, to increase the voltage gain, I can either increase GM or R out. And it turns out that increasing GM is not that easy. But increasing R out is a lot easier. So we decided to think of a topology here that has a higher output resistance and perhaps the same amount of transconductance. And we came up with the cascode amplifier. We saw that in the circuit, the transconductance of the overall circuit is approximately the same as that of the input device, but the output resistance is higher, because we have a cascode structure. And after some simplifications, we saw that the voltage gain of the circuit is approximately equal to the product of two intrinsic gains. So maybe 100, maybe several hundred, depending on how much these values are. So that's encouraging. It says that we can increase the voltage gain of the circuit. Okay. But then the problem was that this ideal current source also has to be implemented somehow. We can't buy an ideal current source. So we said this current source also has to have a high output impedance. Because if this impedance, which is from here to AC ground, is low, then that will lower the output impedance of this overall circuit, this R out, and then the gain will be low. So the best candidate that we had for a good current source, meaning one with a high output impedance, was also a cascode current source. Now in this case, this current source must come from VDD to a node in the circuit, from the positive supply to a node in the circuit. And we know that such a current source has to be a P-type current source. So we went ahead and built a P-type cascode, the PMOS cascode, and used that as the load of this cascode amplifier. And after some simplifications, we arrived at this relationship. So we see that we have two output impedances in parallel. One is the impedance of this cascode, as seen here, and the other is the impedance of this cascode, as seen here. And these two are in parallel because if I sit out here and look to the left, I see one impedance to AC ground and another impedance to AC ground. So the two are in parallel. Okay, so that is the equation for the voltage gain of the circuit. So you can see that based on this understanding and based on some simplifications, we can quickly write the voltage gain expression of the circuit. If we wanted to draw the small signal model for this, and this transistor, it will take a long time to solve that circuit, right? And the net result, the result would not be even as nice as this. It would be something really complicated. So it is this intuition and this gradual build-up of our understanding of the circuit that allows us to quickly write an expression for the behavior of the circuit and also have intuition and insight about what the circuit is doing. Okay, I finished last time with this question posed to you. I said suppose that I have a cascode amplifier, and for the current source that I need up here, this current source, I will use a single transistor with degeneration. And I would like to find the voltage gain of the circuit. Okay? So this is just a practice, some practice in understanding these concepts. And it's not that hard. We're going to say that, well, the voltage gain, as usual, is minus GMR out. How much is the GM? So for GM, we have to put a short circuit from here to ground, right? When we put a short circuit from here to ground, just like what we saw last time for this guy, the load does not matter anymore because the load is shorted out by this short circuit. So the current that is drawn from the short circuit is the one drawn by M1. And the current through M1 is very close to the current through M2. So this current is just GM2 times V in, which means capital GM is approximately equal to GM2. M2 is called the input device. Okay, so that's what we saw last time for this structure as well. All right, now we just need to find the output resistance. So how much is the output resistance? Let's write it here. So we're going to make an approximation for simplicity. The output resistance seen from here consists of two branches in parallel. This N branch going to AC ground and this P branch going to AC ground. For the N branch, we know, right, is approximately given by GMRO of the cascode device times the degeneration resistance or the degenerating resistance. So that would be GM1 RO1 times RO2. That's the resistance seen looking into the NMOS cascode. Now for the PMOS current source, we have a simple transistor that has source degeneration. And we already know the equation for this output resistance, right? That equation reads like this. It's 1 plus GM3 RO3, 1 plus the intrinsic gain of this device, times the degeneration resistance, RS, plus RO3. And again, if we assume that GM3RO3 is much greater than 1, this is approximately equal to GM3RO3 RS plus RO3. So what we see here has to go in parallel with what we see here. So this will be in parallel to this whole thing. So that's GM3, RO3, RS plus RO3. So this is the output resistance of this circuit. Of course, in that situation, all independent sources are set to 0. So this is 0, AC 0. This is also AC 0, and this is AC 0. Okay, so we have found the transconductance of the circuit and the output resistance. So if we just multiply them with a negative sign, we get the voltage gain. So the voltage gain will be given by GM2 times this whole thing with a minus sign. Okay, so that answers last time's question. All right, so today we will start looking at some more examples just so that we have more practice on the Cascode circuit. The more examples we go through, the more insight we'll develop into the properties of the circuit, and then we can use it more easily. I emphasize the circuit because it's still very common. It's a beautiful topology and we use it very often. Okay, so let's see. I'm going to start with this example. All right. So we say example 1. And I would like to look at the circuit here. So V in, V out. There's a bias here, VB. Let's call this M1, M2. And this is an ideal current source, right? Okay. It's a simplified Cascode amplifier because this is still ideal. All right. I would like to study the voltage gain of the circuit under two conditions. Okay, so we're going to write this voltage gain, if you remember from the previous page. It's approximately given by two intrinsic gains multiplied, right? So approximately minus GM1 RO1 GM2 RO2. Okay, so we'll consider two cases. So we'll make a table here. Case number 1. We assume that the bias current of the circuit is halved. So bias current is halved. Halved means it's divided by 2, right? So for example, the bias current was 1 milliampere. Now it's 0.5 milliamperes, okay? Half the current. And we would like to see what happens to voltage gain. In the second case, we assume that the widths of the transistors are doubled. And again, we'd like to see what happens to the voltage gain. Okay, these are two independent cases. Okay, so one at a time. The bias current is halved. All right, so we got to go here and see what happens to these 4 terms when the bias current goes down by a factor of 2. Okay, well, I have to remember some equations here. The equation for GM from Electronics 1, one of the equations, remember we have 3. There are 3 of them. One of them was this, 2 mu n C ox W over L ID. So if ID, the bias current, goes down by a factor of 2, because it's halved, then GM goes down by a factor of square root of 2. Okay. All right, so we say GM1 and the GM2 drop by square root of 2. Both of them are divided by square root of 2. Okay. How about RO1 and RO2? Well, here's another equation we remember from Electronics 1. It was 1 over lambda ID. Again, ID is the bias current, and lambda is the channel length coefficient. So what we see is that if the bias current goes down by a factor of 2, RO goes up by a factor of 2. So RO1 and RO2 go up by a factor of 2. Okay, so this is, I hope it's clear, it's by a factor of 2, right? This is by a factor of square root of 2. Okay, so then what's the net result? What happens here? All right, so let's see. This goes down by square root of 2. This goes down by square root of 2. So the net result is 1 over 2. This goes up by a factor of 2. This goes up by a factor of 2. So I'm going to write it like this. GM1 over square root of 2. 2 RO1. GM2 over square root of 2. And then 2 RO2. So we see that these two will give us a factor of 2. 1 cancels this one, we still have 1. So the total voltage gain goes up by a factor of 2. So AV goes to 2 AV. Okay, in this scenario, when the bias current is halved. Okay, that's great. How about the second scenario? Here, we are assuming that the width of the transistors is doubled, both of these. And we'd like to see what happens. Only the current is constant. Okay, so we go back here. GM has this dependence. So because the width is doubled, each GM is multiplied by square root of 2. Okay, so we're going to write square root of 2 GM1 because the width has gone up by a factor of 2. How about RO1? RO1 does not have a dependence on W if the current is constant. So RO1 does not change. GM2 goes up by square root of 2 because this W has gone up by a factor of 2. So square root of 2 times GM2, and RO2 does not change because it does not depend on W if ID is constant. So that's RO2. So now what happened? In this case also, the voltage gain has gone up by a factor of 2. So we see that AV has gone up to 2 AV. Okay, so that's an interesting trend that we see. Depending on how we choose our dimensions, etc., we can play with the width of the devices, we can play with the bias current, and adjust the gain in some direction. Okay, so let's go to example 2. And in this example, we'll be more ambitious and we'll replace this current source with a PMOS cascode, like what we had here. So now we have this situation. Let me try to draw it on this side. So V in goes here, V out goes here, and we have M2, M1, M3, M4. Okay? And we want to perform the same experiments. So we're going to have the bias current in one experiment or double the width of the transistors in the other experiment and see what happens to the voltage gain. Okay, so I need to write the voltage gain for the circuit, and I saw that on the previous slide, in the review slide. So what we have is this. The voltage gain is given approximately by the transconductance of the overall circuit is the same as that of M1, approximately, right? Because the current generated here flows all through M2 mostly, and then flows through that short circuit. So we have minus GM1. Okay, sorry, let's call this M1 and M2 just to be consistent. So GM2. Okay, and we need to find the output resistance. And we said that there's a resistance looking up, there's a resistance looking down, and those are in parallel. So we have, looking down, we have GM1 RO1 times RO2 approximately. GM1 RO1 RO2. And then looking up, we have GM4 RO4, the intrinsic gain of the Cascode device, times the degeneration resistance RO3. Okay, so that is the overall voltage gain of this more realistic Cascode amplifier. And our objective is to determine what happens to this gain as we play with bias current or the width of the transistors. Okay, so no problem. Same situation as before. So we say ID goes to ID over 2. We have the bias current, or all W's. We have all W's here, right? All W's go to W2s, W over 2s. So we have 4 W's, all 4 W's will be reduced by a factor of 2. Okay, so in each case, we want to see what happens to the voltage gain. All right, so when the current goes down by a factor of 2, as we saw before, each GM goes down by square root of 2. Each RO goes up by a factor of 2. So what we have is this. I think I need more room here. Let me change the color of my pen so that we have, so let me write it here. So we have minus GM2. The current goes down by a factor of 2. The transconductance goes down by a factor of square root of 2. So minus GM2 over square root of 2. Okay? All right. Then we go in here. GM1 gets divided by square root of 2. But RO1 and RO2 are multiplied by a factor of 2. So we have GM1 over square root of 2. And then times 4 RO1, RO2. Because each of them is multiplied by a factor of 2 as we saw before here. All right. And now, in parallel with that, we have the second expression, which is the same situation. So it's GM4 over square root of 2 times 4 RO4 RO3. Okay, so this is what happened after we reduced the bias current by a factor of 2. All right, so what's the net result? What can we say here? Well, okay, so think of these two resistors. This resistor is multiplied by a factor of 2 over square root of 2. Okay, so this is multiplied by 2 over square root of 2. And similarly this one. So this is also multiplied by 2 over square root of 2. So if we have two resistors, not necessarily parallel, just two resistors, not necessarily equal, just two resistors in parallel, right? And each of them changes by a factor of alpha, what happens to the net result? The parallel combination also changes by a factor of alpha. So this changed by this factor, this changed by the same factor, so the parallel combination will also change by the same factor. In other words, we can factor this out. Okay? So then we have minus GM2 over square root of 2 as before. We factor this out, 2 over square root of 2. And then we have the original number. So we have GM1, RO1, RO2. And then the whole thing parallel with GM4, RO4, RO3. Okay, I made a mistake here. This should be 4 over square root of 2. This should be 4 over square root of 2, right? So then this is 4 over square root of 2. Okay, so the net result is that these two give us a factor of 2. this goes a factor of 4, so the net result is a factor of 2. So we see that AV goes to 2AV. So in other words, whether we have an ideal current source here or an actual cascode, changing the bias current by a factor of 2 changes the gain by a factor of 2 in both cases. Right? That's interesting. All right. For the case on the right-hand side, meaning we change the W's by a factor of 2. Sorry, I meant the W's are doubled, so this should be 2 here, not here. 2 W's. All the W's are doubled. So for this to happen, we go back and see exactly how the values change. So we said that GM goes up by square root of 2, but RO does not change. Okay, so then what can I do? Because I'm too lazy to write all of this again, I'm going to just make the changes right here in red. You can just write it out. So GM2 becomes square root of 2 GM2. So this is a factor of square root of 2 because W has gone up by a factor of 2. GM1 also goes up by a square root of 2. RO1 and RO2 do not change because they do not depend on W for a given current. GM4 is multiplied by square root of 2. RO4 and RO3 do not change. So now what happens? I can factor out the square root of 2 from here and then multiply by square root of 2 here. The net result is also a factor of 2. So in this case, as well, AV goes to 2AV. So again, it has the same behavior as the more idealized cascode amplifier. So whether this is an ideal current source or it's a cascode current source, as long as we change all of the W's together, the overall voltage gain changes by a factor of 2. All right, so that gives us some better understanding of this topology. Okay, so let's now look at another example. So I want to give you a little quiz. Let's go to the next page and see what we can do here. Okay, so here's the quiz of the day. So let's go back to that idealized cascode amplifier for simplicity. And we have a cascode structure here. And what we do is we apply the input to the gate of this bottom device. We apply a bias voltage to the gate of the top device. And the output is taken here, right? Okay, but let's say when we were constructing the circuit, we made a mistake. And what happened was we mistakenly connected the input to here and connected bias here. And this is M1 and this is M2. So we would like to find the voltage gain in this case. Okay, so how much is AV? All right, I'll give you 1 minute to think about that. All right, so what do you think? Well, we would expect that the gain should be pretty low. Why? Well, so we go back to our general equation. Let me change the color of the pen. So we have AV equals minus GM R out. Okay, so one at a time. Let's look at R out first for simplicity. Does the output impedance of the circuit depend on whether the input is connected to this gate or to this gate? The answer is no, because when we are calculating the output impedance of the circuit, we are sitting here applying a small signal voltage Vx and measuring the resulting current Ix. We need to set all independent sources to 0. This is AC ground and this is AC ground in that test. So we don't even know where the input was because the input has to be set to 0. So the output impedance of the circuit does not depend on whether the input is connected here or here. Okay, so the output impedance does not change by this mistake. But how about GM? Okay, so let's construct a circuit for GM and see what it looks like. Here's what we have. This is AC ground, right? Because it's a bias, it doesn't change with time. This is our input. We place a short circuit to ground and we are measuring this current, and the ideal current source has become an open circuit and vanished. Okay, so this is the environment, right? And we would like to find I out over V in as the transconductance of the circuit. Okay, so how do I do that? Well, it's just a little circuit that we have. We haven't seen the circuit before, but it's okay. We're just wondering how to solve the circuit. Well, we know one thing. What is the role of M2 here? M2 is a constant current source, isn't it? M2, these are all both in saturation. M2 is a constant current source. It has certain constant gate source voltage. So when we have a constant current source for small signal analysis, we can replace it with its output resistance. So this reduces to just an output resistance. So what we really have is this. So far so good? Okay, so now if we want, we can calculate the transconductance of the circuit. For this, we probably have to draw the small signal model if we want to include the output resistance of M1. Okay, so if we do, we could do that, but let me for a moment not worry about the output resistance of M1, just as an approximation. You may like that approximation or not, it's okay. I just want to make a point, okay? So let's assume RO1 is infinity, okay? Now this may not be a very good approximation, and that's okay, okay? Just to make a point. All right, so then we know how to find the transconductance of a transistor that is degenerated. We know that from Electronics 1. So GM is given by, you can prove that easily, is given by the original GM that we had without degeneration when this is 0. That was GM1. And because of degeneration, the transconductance goes down. And it goes down by a factor of 1 plus GM1 times the degeneration resistance. RO2. So let's digest this for a second and see exactly what happened. So when we had the good cascode, meaning V in was connected here, the transconductance of the circuit was given by GM2 approximately, right? Because it was this transistor that converted the input voltage to a current. Now that we have this bad cascode by mistake, what we see is that the transconductance of the circuit, meaning from here to the output current, is given by GM1 but reduced by a pretty large factor, 1 plus GM1 RO2. This is about an intrinsic gain, so it's reduced by a factor of maybe 10. Okay, so what we can say is that reduced considerably and in this equation we see that the transconductance of this circuit, this bad circuit, is reduced considerably because this device is heavily degenerated by this device, right? So this is very low, this hasn't changed, so the overall voltage gain has dropped considerably. So as a result of this mistake, if we measure the gain of the circuit from here to here, it will be quite lower than the good Cascode when the input was here and the output was here. Okay? So we articulate this as follows. We say the gain, or the voltage gain from the gate of the Cascode device to the output is very low. Okay, it's good to remember this. Sometime in your future you're going to need this because there are some other circuits and considerations that come into play, and it's good to remember this, that the gain from here to here is not very high. The gain from here to here is high, right? It's given by GMRO of this times GMRO of this approximately. But the gain from here to here is not very high. We haven't actually calculated the gain, but we just say that it's not very high. Okay, so that was only the purpose of this quiz. Okay, let's talk about Cascode amplifiers with P-type input. So for that I need to build a little background for you. So let me make an observation here. So let's not worry about Cascode for a moment and just think about the circuit. You know that we can build a common source amplifier like this, V in, V out. Now, because I cannot buy an ideal current source, I have to implement this by a P-type current source, like a PMOS. So I will have to build a PMOS current source and connect it here. This is V in, V out, and this is a bias. So far so good, right? You've seen this before in Electronics 1. Okay. Now, let's suppose that so let's number these. We call this M1 and M2. Now, this common source stage has an input transistor, which is an NMOS device. Now, we could build a common source stage whose input device is a PMOS transistor, right? That's perfectly acceptable. So for that, I would draw it like this. V in, V out. This is connected to VDD. Right? Is that okay? Again, this transistor senses a voltage at its gate. Its source is connected to AC ground. Of course, this is necessary for proper biasing. And as a result, it generates a current in proportional to V in. And that current flows through RO and generates a voltage. And that's what we get. Now again, I have to implement this because I cannot buy an ideal current source. This current source goes from a node to ground. So that would be an N-type current source. So I would have to build something like this. Okay, so let's give these numbers. I'm going to call this M2, M2, and M1. So both of these are common source amplifiers. One has an NMOS input device, one has a PMOS input device. So by the time we are over here, these two look awfully similar, right? The only difference is, in one case, the input is applied to the gate of the NMOS, and the PMOS acts as a current source. In the other case, the input is applied to the gate of a PMOS, and the NMOS acts as a current source, right? Otherwise, they're the same. All right. Is the voltage gain of the circuit the same as the voltage gain of the circuit? No. So let's ponder that for a second. All right. How much is the voltage gain of the circuit? Okay, so remember this expression here? Again, it comes in handy. So I will write AV equals the transconductance of the circuit. So again, in your mind, place a short circuit to AC ground and see how much current flows through this in the small signal model. This guy is out of the picture. Okay, doesn't produce any current, it's out. So what we have is a current flowing here, which is given by GM1 times V in. So that's GM1 with a negative sign. How much is the output resistance? The output resistance, I sit here, I look up, I see the output resistance of an PMOS device to AC ground. I look down, I see the output resistance of an NMOS device to AC ground. So this will be RO1 in parallel with RO2. And again, this is something we have seen in Electronics 1. And again, anytime in doubt, you can draw the small signal model of these two and work out the equations and see that that's what we get. What we do know is that this constant current source reduces to only a single resistor in the small signal model because this gate source voltage is constant. So the internal dependent current source, the small signal current source, is 0. So what's left is just RO2. Okay, and then we have RO1 from this one. So that's the output resistance. Okay, that's great. How about the voltage gain of this circuit? All right, well, same principle. AV equals minus the transconductance of the circuit. This time, the input goes to the gate of M2, which is a PMOS device. So this has its own transconductance, and that current comes out and goes through the short circuit in test A. So that would be minus GM2. And then the output resistance. How much is the output resistance here? Is that different from the output resistance here? No. These are the same. Because to calculate the output resistance, I would do something like this, right? Vx and Ix for both of these. When I do that, I have to set all independent sources to 0. This will be AC0, 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 AC0. So these output resistances will be the same. So this will be just RO1 in parallel with RO2. Okay, so let's digest this for a second. What we see here is that the voltage gains are different because the GMs of these two transistors are different, right? All right, so now we're going to extend these ideas to the Cascode device with the PMOS input. And in fact, for that, I will just go back to the first slide, see if I can squeeze that in here. Okay, so remember this structure that we had before? We analyzed the number of times. So the input goes to the gate of an NMOS device and generates a current. And that current flows through this and so on. Can I apply the input instead of here to here? Okay, so if I call these M1, M2, M4, M3, what I see is that, yes, this is also a perfectly legitimate cascode. Now, the PMOS structure is acting as a cascode amplifier, and the NMOS cascode is acting as a constant current source. Okay, that's perfectly fine. We can do that. All right, how does the gain of this circuit differ from the gain of the original circuit or the gain of this circuit? Okay, so let's go back to this expression. Remember, we derived this for this circuit or the black circuit. What do I have to change here to make it valid for this PMOS input? All right, so again, we have the transconductance of the circuit and the output resistance of the circuit. The output resistance does not change. It doesn't matter whether the input is here or here. The only thing that changes is the transconductance. Previously, the transconductance of the circuit was that of this guy, which we call GM2. Now, the transconductance of the circuit will be this guy because it is this transistor that converts the input voltage to a current. So it generates a current here, which would be GM3 V in, right? So all I need to do is change this to GM3. The output resistance is the same, so the voltage gain changes to GM3. This is an example of a cascode amplifier with PMOS input as opposed to NMOS input. Okay, it follows exactly what we saw for common source stages with PMOS and NMOS inputs. All right, this concludes the lecture. I will see you next time.